Okay, so welcome everyone to live session 4 for design and analysis of VLSI subsystem. The course has been taught by Professor Madhav Rao. And I am Kailash Prasad, PhD scholar from Nanoelectronic Devices and Circuits Lab. So this session is held every Tuesday, 7 p.m. to 9 p.m. And the goal of the session is to solve the questions which has been will be helpful in understanding the concepts which has been taught in the class. Along with that, we'll be discussing some of the questions which will be relevant for the interview preparation for you guys, and couple of more questions focus on basic understanding of VLSI design. So we will start today's session. So as of now, what we have done in last 4 or 5 sessions as we have discussed about CMOS transistors with basic current model, then we have discussed about inverter and the characteristics of the inverter. Further, in the last session, what we have discussed is about the noise margin and the delay of the inverter. Okay, this session will be majorly focused on RC delay. Along with that, as discussed in the last class, right? I'll be going to week 5 also. Some of the questions I will take from the logical efforts also. Okay, so the goal is I will try to catch up with the class such that maybe by the next session we will be having all the discussions regarding a particular topic such that it will be helpful in submitting your assignment also. Okay, so I might not be able to catch up today, but surely in the next session, by the next session, we'll be ahead in that regards. Okay, so we will start today's class with a very basic question, right, on the capacitor. See, this is a circuit. This is a digital circuit. Can anybody tell me what this circuit is?
Buffer.
It's a buffer. Okay. So this circuit is nothing but a buffer. So two back-to-back connected inverters are there. Okay. Now, the question that has been asked over here, there's that this is point X. Okay. At this particular point, which of the capacitance in the diagram will affect the propagation delay of node X? So X will have some propagation delay because the capacitance are associated with it. So many capacitance are there, C1 to C12. The question over here is which of the capacitance will affect the propagation delay? Can anybody tell me the answer quickly? There's so many options, and it's a multiple select question. Okay, anyone?
Four, five, C4, C5,
C4, C5, and
C7, C8,
C7, C8. Okay, thank you.
C7, C8.
Okay, so the thing that's the correct answer. So the answer is C4, C5, then C7 and C8. Okay. Now why this is the answer? That's the question. So if you see over here, this particular node, this X is connected to drain of P1, then drain of N1. Okay. Then it is connected to gate of P2 and gate of N2. So when you try to find out capacitance, okay, which capacitance will contribute to that particular node, you have to understand, okay, what are the nodes I am connected with. This X is connected with 4 nodes: drain of P1, drain of N1, gate of P2, and gate of N2. Okay, so the capacitance which is associated with drain of P1, if you see over here, this is C4. Okay, the capacitance which is associated with drain of N2, this is C5. Similarly, the capacitance which is associated with the gate of P2, this is C7, and similarly the capacitance which is associated with the gate of N2 is C8. Okay, so the answer over here is C4, C5, C7, C8. Okay, so C4, C5, C7, C8. So the answer will be D and F. Okay, any questions in this part? Any questions? Okay, no question, then I will proceed ahead. Okay, I just wanted to remind you from the previous class why these capacitances are very important. Okay, we have discussed in last class. We had a quick discussion over there that if you want to say minimize the delay of your circuit, what should you do? There were few arguments. One of the argument was, okay, what I can do, I can increase the width. Okay, so I can increase the width of the transistor. So that was one of the argument. Okay, why this was an argument? If you increase the width of the transistor, what will happen? The current increases. If current increases, the delay reduces. Okay, now the second point which we have discussed over there in the last class was, you have to decrease the width of the transistor. Okay, so the first argument is increase the width of the transistor. The second argument was decrease the width of the transistor. Decrease the width. And what was the logical reasoning behind that? If you decrease the width of the transistor, what happens? This parasitic capacitances actually decreases, right? Because these capacitance are nothing but directly proportional to the width of the transistor. Okay, so that was the argument. So the capacitance will go down. Okay, so the thing is, if you increase the width of the transistor, I increases, means R go down. Okay, but if you decrease the width of the transistor, so C goes down. So then we have discussed in the last class that, okay, let us plot this. Okay, if you plot this over here, what happens if this is width? Okay, and what I am trying to do, I am trying to increase the width of the transistor. If you increase the width of the transistor, what we have observed, that the capacitance increases like this. Okay, similarly, if you increase the width of the transistor, if you see the resistance decreases. Okay, then we have discussed in the last class that, okay, if I want to say optimize, if I want to optimize the delay of my circuit, I have to have a point where both capacitance and resistance are actually minimum. We have to figure out the RC of the transistor rather than focusing on R and C. Okay, so this particular session is actually focused on RC delay, right? Because not only R or not only C, individual contribution of them is not important, rather the total, the combined effect is important for us. Okay, and how does it will affect? It will affect in a great sense. Okay, so as of now, in the classes, I guess we have not discussed about power. So I think in one of the lectures, the power will be discussed, and we observe that if you increase the capacitance, the power increases, right? If you decrease the capacitance, the power decreases. Okay, similarly, if you increase the capacitance, delay increases. Okay, if you reduce the capacitance, the delay decreases. Okay, so the two important metric of any digital design is what? One is latency. Latency means speed, how much time it is taking. The second is power. Okay, and both of this power and speed actually depends on R and C both. Okay, and that is the reason why we will be focusing on R and C in today's class. Okay, how do you design a circuit? In the circuit, RC is minimum. Okay, so we will move to second question. uh, it's okay, I think I moved too far. Yeah, first we will move to second question. In this question, the question is very simple: which of the following are true regarding the effort of a logical gate? Okay, so this the question over here is, if you have a gate, right, and if you are finding logical effort. Okay, logical effort is denoted by G. Okay, so if you find the logical effort, or the logical effort depends on what factors. Okay, so you have from A to H, total 8 points. You have to answer which of this point will correlate with the logical effort.
E.
Okay, I have an argument E is one of the thing. It's a multiple select question. Do you think any other answers are there? Anybody else? Anyone?
H.
E. Okay, I have another answer A.
H.
H. I have another answer H. F. Aditya is saying F also. Okay, F. Anybody else? Okay, so let me try to answer this. Okay, so E, F, and H are the answer which I have got. See, one thing you have to realize when you calculate the logical effort, that whatever logical effort you get, you actually normalize with the inverter value, right? So the logical effort actually directly depends on the inverter, whatever the inverter is. Okay, so if you see the first argument, the delay of the standard inverter affects the value of the logical effort. So that's the correct argument, right? Because if you want to calculate the logical effort of any gate for any input, what you do, you normalize with the inverter, right? If the delay of the inverter changes, the size of the inverter changes, then the logical effort will also change. Okay, so A is the correct answer. Now let's move to the B. The logical effort is an indication of the number of standard inverters that can be driven, right? So the question over here, or the point what it is trying to say, that if you know the logical effort, can you tell me that okay, how much is inverters it can drive? The answer is no. You cannot tell anything about that using the logical effort. Okay, so B is not the answer. Now moving to C, what C is saying, the logical effort is a function of output load capacitance of the logical gate. So this is also not correct, right? Because it's a function of input, not output. Okay, so the fourth question, 4 point will be correct, right? The logical effort is a function of input capacity, right? So in that regard, the fourth question will be correct. The logical effort is a function of input capacitance of a logical gate. Okay, now moving to E, the logical effort is an indication that the relative ease difficulty of driving a logic using a standard inverter. So the thing is, whenever you calculate logical effort, you normalize with the inverter, right? So actually what you are trying to say, that as compared to inverter, how good your gate is in driving a particular load. So whoever has said E answer, so that's also a correct option. Okay, now moving to F part, the logical effort of a logic gate depends on the number of logic gates connected to its output. The answer is no. So this is not correct, because the logical effort only depends on input, not output. Okay, so it doesn't matter how many gates you connect at the output. The logical effort of the gate remains the same. Okay, G point. The logical effort of a logic gate depends on the type of logic gate connected at one of its input. No, right? It doesn't matter what type of logical gate is connected, right? So this is also not correct. And the logical effort of all logic gate depends on the type of logic gate. So no, the type of logic gate has nothing to do with the logical effort, right? Logical effort only depends on the input capacitance of that particular logical gate, and whatever the size of the invert, or sorry, the logic you have, you will calculate the logical effort. Okay, so now what I will do, I will just make a gate and I will quickly ask you to tell me what kind of logical effort this gate will have. So let me make some gate. So this is a gate, okay, some gate. Please tell me what gate it is, and if I want to find out the logical effort, what is the first step I have to do?
It is a two input NOR gate.
It is a two-input NOR gate. Okay. Then if I want to find out logical effort of this gate, what should I do?
First to calculate the input capacitance of this gate, or first to calculate the width W.
Okay. How do I calculate the width?
1/2 is out by
1
So
by
it is
UP by mu n
uh,
is 1 by 2. That's correct. So what
oh,
should I do?
actually the width for PMOS will be 4 and for NMOS will be 1.
Okay, this will be 1 and this will be 4. You're saying like that?
Yes, yes, yes,
Okay.
exactly. Then input capacitance is 5 and the logical effort will be 5 by 3.
Okay. Input will be 5. Input C.
No, 5C, 5C,
Okay, 5C. Okay. So G will be 5C by 3C. So it will be 5 by 3.
5 by 3, exactly.
So can you tell me how do you come up with this number 1 and 4?
Okay, actually, for a standard inverter, it is 2 by 1. Normally, the width is 2 by 1. Now, when we calculate the switching resistance using that equation, that is for PMOS, it is 2R by W is equal to R. So, where W is equal to 2, here it is R is equal to here, the switching resistance for individual PMOS is R by 2. So using that formula, we get the total resistance will be R. So equivalent resistance for one is R by 2. So W will be 4. And
Mhm.
for NMOS, it is Rn will be will be R. So it is 1.
Okay.
So actually, it is a trick I use that whenever the PMOS in the series, then it will increase by 2 factor, and when the NMOS in the series, then it will increase by 1 factor.
Okay. Yeah. Thank you. So let me tell you what he was saying, and let me try to make you understand. Whenever you want to calculate the logical effort, what you should do. Okay. So see, this particular design is actually divided into two parts. Okay. So the first part is the pull-up network. Okay. The second part is pull-down network. Now the question over here is what we try want to do what we want to or what we are trying to do here is the resistance of the pull up path and the resistance of the pull down path should be same. Okay, so that's our argument. So whenever you want to make like that, right, the first thing you see in the pull down path, right? In the pull down path, you have an NMOS, and NMOS has higher mobility as compared to PMOS, right? So it is understood that the NMOS will take lesser width as compared to PMOS. Okay, so then what we will do, we will start with the minimum width which is available to us. Okay, and if you see both are in parallel, okay, both whenever two transistors are in parallel, actually you have to focus on one path and then you focus on the other path. Okay, so I will forget this particular path for now. Okay, so what I will do, I will put one over here. Okay, so if one is the width, right, so R of NMOS is directly proportional to W, right? So it is 1 W. So 1 means 1 times W. Now what I have to do, I have to make sure that the upper part resistance is also uh, same. Okay, so Rn and Rp should be same. Now I have to upsize or whatever I have to see. Okay, now if you see there are two transistors which are in series. Okay, so if this one has resistance R, okay, if this has resistance again R, so the overall resistance will be 2R. So that's the first point. Okay. Along with that, the mobility of the PMOS is also two times, or sorry, 1 by 2 times of your NMOS, right? So first, what happened that the resistance has become 2R because of increasing the stack, right? Because transistor are in series. And the second point is mobility of N is 2 times of mobility of P. So if I have to compensate that, right, I have to again multiply it by 2. Okay, so I have to multiply it by 2 and 2, so the number will come, that will be 4. Okay, so individual transistor should be actually 4W, both of them, in order to make sure that the resistance of pull down and pull up path is same. Okay, so there from there the number comes 4 in the case of NOR gate, this two input NOR gate. Okay, so this part is 4, so this part is 4, so you can assume that normally the resistance of the unit PMOS is actually 2R, right, as discussed by him, right. Why it is 2R? Because the mobility is 1 by 2 times, right. If mobility is 1 by 2 times, so resistance has increased 2 times. Okay, and this also it is 2R, right, and here the resistance is R. I have to make sure that the total resistance should be how much? The total resistance should be R. Okay, so not 2R. Uh, yeah, I think I'm doing it wrong. So it will be 1 by 2R, 1 by 2R. So you have to calculate like this. Okay, then the actual resistance will be inverting of that. It will be R, and then what you will do? You will add from here, right? And the total resistance will come R over here. Okay, so this is how you will calculate actually the logical effort. When you want to calculate the logical effort, the first thing you have to make sure that the pull down and pull up path is of the same strength. You have to size. Okay, the first step is you have to size. Once you size, then you take any of the input, and then what you have to do, you have to calculate the equivalent capacitance. Along with that, what you do, you divide using standard inverter. Okay, so if I see over here, if I remove this particular part, so I will just redraw everything again simply. Okay, so this is 4, this is 4, this is 1 1. Okay, you have to make sure that every path has that same particular ratio, right? Because it can happen that if this is A, this is B, if this is A, this is B. Okay, it can happen that this is off, right? So the equivalent the resistance of this particular path should be same. Okay, that is the reason why we do not make it 1 by 2, right? You make it 1 only. Okay, or you don't make it 2, right? You make it 1 only, right? So now if you see A has how much input capacitance? 4 of this, 1 of this, so 5. Similarly, so this will be C of A, okay, 5C. Then C of B will be 5C. Okay, and if you want to calculate for the logical effort, then what you have to do, you have to make sure that your inverter is there. So this is your unit inverter. Okay, so in the unit inverter, life is very simple. What you have to do, the NMOS will be of one size, the PMOS, which will be how much times? 2 times. Okay, 2 times of that, so this is 2. So C of inverter will be 3 over here, right? Because 2 plus 1. So if you calculate logical effort of this particular gate, this will be C G of A, this will be 5C by 3C. Okay, this will be 5 by 3. Similarly, G of B will be 5C by 3C, again 5 by 3. Okay, so here GA and GB both are same. So if that is clear, I will give you one more gate, and you just quickly tell me what will be the logical effort, right? So I will understand that everybody has understood the concept. So let me make another gate. Okay, so please tell me what will be the sizes over here, and then you tell me what will be the logical effort. What will be the sizes of NMOS and PMOS?
2.
Sorry.
For PMOS it is 2, for NMOS it is 2 size. And the
Okay.
logical efforts is 4 by 3.
So you are saying that everything will be 2. Okay.
Yes.
What about others? Everybody agrees with that? Other students? You can comment, right? You can comment if you agree with this. Okay, Momita is agreeing. Okay, so yeah, that's correct. Okay, so it will be 2 2, right? Because the equivalent of the 2 2 will be 1, right? And then 2 and 2 are in parallel. So if you take any one of the path, right, it will be 2 by 1. Okay, so that is our mobility ratio. Now, the inverter, if you take, so inverter had 3C, it will have AA, so it will be 4C by 3C. Okay, so the answer will be 4 by 3. Now, the question over here is, so this is one question which is generally asked in interview, right? Uh, if you want to design, say, full adder, okay, if you design a full adder using NOR gate and NAND gate, which gate you will use to design the full adder?
NAND, definitely.
What is the reason behind that?
The logic effort for NAND is less than the logic effort for NOR gate. It is 4 by 3, and for NOR it is 5 by 3. Same input, two input. So definitely we will choose the NAND gate.
And how does it will help us? Logical effort is less. So what will happen if I
Yes, actually propagation will be less for this because the propagation expression, it have the logical P plus G into H. So if G decreases, G less, then the overall delay will be less.
okay, okay. So Momita, do you want to say something? Okay, so yeah, that's correct answer. So the thing is, if your logical effort is less, right? So the delay will be less. Okay. So in the case of NAND gate, G was how much? 4 by 3. Okay. In the case of NOR gate, the G was 5 by 3. Right. So that's a straight away answer. Now, if you see the area, the how much area it will take, or how many number of transistors you have, or so if you see here it is 2W, here it is 2W, 2W, 2W. Total area will be around 8W. Okay, so this is not a correct, please understand, this is not a correct area calculation, but I'm just saying that, okay, if I have transistor of 1W, how many transistors I will take? 8 of those. Okay, but in the case of NOR gate, I had 4 plus 4 plus 1 plus 1, right? So the area wise also, it was 10W. So you will get benefit area wise also, delay wise also, both. Okay, so in that regards, your NAND gates become preferable as compared to NOR gate. Okay, so if anybody asks you this question, then you have the answer of this. Okay, please ignore this part. Any questions in this regard? Okay, so I will move ahead. A simple question. So find the delay of the output node of the circuit using Elmore delay. Okay, and you have to enter the correct answer over here. So let me just redraw this circuit. I will quickly solve this particular problem. So if you see this particular C, so here it is R, this is R, so this will be R by 2. Okay, if you see this is R, this is R, this is will be also R by 2. Okay, then there is another R, okay, which is not connected anywhere. Okay, so this is C. Okay, so this is R. Then what do you have? Then another C. Okay, then this is R, and then another C. This is your output. Okay, so this is actually ground. Now if you apply the Elmore delay formula, right, you have to see, right? So the thing is this, if this is the node which I'm looking into, okay, so here it is ground. Okay, so I will start from here, and whatever we are getting in the off path, we will just add the RC of that. Okay, so from there to there, if I try to calculate, or if I go to reverse direction also, right? So the formula how it will be, so the Elmore delay, delay will be, so this is our resistance with this particular capacitance, which is off path. Okay, so this is not in the path, this is off path, this particular one, this is off path, because the path is this, if you see, right? So this will be directly added R by 2 into C. Okay, now you will have to see all the on path resistance. Okay, so here R into C, so all of these are C. Okay, so this will be R into C. Okay, plus for this particular capacitance, what is the resistance to the ground? So this, the entire resistance is to the ground, so R plus R by 2. So this will be R plus R by 2 times C. Okay, if you see this particular capacitance, what is the resistance to the ground? This R plus this R plus this. Okay, so this will be R plus R by 2 plus R times C. Okay, so if you calculate over here, this will be R by 2C plus RC plus R by 2, 3R by 2C plus 2R, 4. So this will be 5R by 2C. Okay, and if you add all of this, I think, so just let me check if I have done everything correctly. Okay, so yeah, everything is correct. So R by 2 plus 3R by 2, so this will be 4R by 2, 4R by 2 plus, so that will be 2R plus R, 3R, 3RC from here, and here 2.5 RC. Okay, so this is 5.5 RC. Please confirm if I am correct or not in this regard. Okay, Aditya is saying yes. What about others? So this is how Elmore delay works. Okay, so whatever output node you have to find the path to ground. Okay, in the resistive part to ground. So this is the resistive part to ground. Okay, and whatever resistance which is not coming in the path, right? So that will be your off path. So off path will be directly added. So R by 2 into C of that. Okay, and in on path, you just keep on adding resistance and capacitance. Okay, whatever capacitance you have, you just see what are the resistances which is to the ground, right? That's how the Elmore delay works. It's a very famous equation, or has been given very long back, right? Still been used. Uh, so if you want to say quickly find out, okay, what is the delay of the circuit, Elmore delay will help you in quickly. So it is an approximate equation. Don't You have to note that this is not an exact delay equation. It will be an approximate delay equation because it is linearizing everything, right? But this thing actually you have to keep in mind whenever you design circuit. There are a lot of non-linear effects will also come into picture. Okay, so it might happen that, okay, if you calculate some delay using Elmore delay equation, and if you calculate some delay using cadence tool or spice level tool, you might observe small deviation. That small deviation will come due to the nonlinearity which is there in the circuit. Okay, any question in this regard, this question?
Yes, I have one question. That the first capacitor, the output end, the capacitor,
Yes.
that capacitor actually contribute the RC. That capacitor and the adjacent resistance that will provide the RC in Elmore delay. First is the R by 2 into C.
For
That
this
understood that.
this you understood.
Yes, yes, yes. Next one.
This one, if you
Yes,
see
next.
this capacitance, this will be discharged by this path, right? So this
Okay.
will be RC. Similarly, if you see this particular capacitance, this will be discharged by this path. So R plus, so R by 2 plus RC. If you see this
Yes,
capacitance,
yes,
it will
yes,
be,
yes.
you have to just see the discharge path. So if resistance is in the discharge path, so that will be contributed. You cannot discharge from here because there is a capacitor, right?
Yes,
If there was
definitely.
no capacitor over here, everything will come into parallel and you will have an equivalent capacitor over there.
Alpha 2 into C. Okay.
Okay. If you still have any question, right, you can drop a message in the WhatsApp. Okay, we can see over there. Have you solved this kind of problem and you're getting a different answer? Okay. So now what I will do, I will go to the next question. Fourth one. Again, a very simple one. Okay. So if you read the question, I will read it for you. In this circuit diagram given below, so not given below, given in the right side, the worst case propagation delay, both rising and falling. You have to find the worst case propagation delay. So what you have to find? TPDF. Okay. Then you have to find TPDR. Okay. Use Elmore delay model in this question. Okay. So that's the question that has been given. So whenever you want to find the delay of the circuit, the very first thing what you have to do, you have to size the circuit. Okay. So everybody please tell me the size of all of this transistor P1, P2, P3, P4, N1, N2, N3, N4 quickly. Anyone want to tell me the answer? What will the size? I'm not asking the final answer. The size of P1, P2, P3, P4, and N1, N2, N3, N4.
N1, N2, N3, N4 will be 2. And P1, P2, P3, P4 will be 4.
So that is correct. Absolutely correct. So all of this will be 2. Okay. And all of this will be 4. Okay. Because if you see 2 will contribute to 1, right? The 4 will contribute to 2. Eventually it will come the mobility ratio. Okay. 2 is to 1. So in this manner you have to design the circuit. Okay. Now if you have the size, what you have to do, you have to find out propagation delay falling, then you have to find out the propagation delay rising. Okay. So before that, so what you have to do, you have to find out, okay, what are the capacitances. So we will quickly see what are the capacitance over here. Okay. So how to approach this problem? First, you see all the nodes. So this is one of the nodes. There we will have capacitance. Okay. This is another node. There we will have capacitance. Okay. Then we have two paths. Okay. So there we will have one capacitance. Here also we will have another capacitance. Okay. So if you see over here, this particular node, how much capacitance we will have at this node? How much capacitance we will have? 6. Okay. I'm asking about this node. Okay, so it won't be 6 actually, it will be 2, because whenever transistors are stacked like this, generally whenever we draw the layout, you have to just keep this in mind, because when we discuss about layout, we will come to this particular point. When you design the layout, you diffuse these two nodes. Okay, whenever you diffuse the ideally it should be 4, 2 plus 2, 4, right? But if you diffuse or if you keep one above another, right, the equivalent capacitance will be the maximum of the two. Okay, so this will be 2C. Similarly, this will also be 2C, right? Similarly, if I go over here, right, so I have, so this 4 and 4 will actually give only 4. Again, this 4 and 4 will actually give only 4. So instead of 16 over here, 4 plus 4 plus 4 plus 4, how much we will have? We will have 8. Okay, so this will be 4 plus 4 C. Okay, this is 2C. And if you see the output node, over here. Here it is 2, here it is 2, there it is 4, here it is 4. Now you can ask a quick question, right? That, okay, what will be the output capacitance over here? Because here in this node, I have said that, okay, you can diffuse and you give
12C it
it will be
is.
12C. Okay, it will be 12C plus 2. You are saying that it will be 12C. But I have a question. The question is, because I have said over here you can diffuse and you can have an equivalent of 4 plus 4 and 4. Why not here? Why are you
One
still?
is P type and one is another one is the N type.
So what will happen? Why if one is P type and one is M type?
Actually, for N type, the for N type that source for the N type will act drain for the P type.
Okay,
So then that cannot be, so that's why it may not be diffused. I think
okay, okay.
this should be able to separate. Okay, okay, you can.
Okay, yeah, let me answer you for that. So actually that is not the answer. So whenever you design a standard cell layout, so see, this is a standard cell, okay? So standard cells are the cell which are present in any of the technology library. Basic AND gate, OR gate, NOR gate. This is what is this? AB plus A bar B bar. So it's the XNOR gate, right? So all of these gates are generally found in library. These are called as standard cells. So whenever you design the layout, okay, how do you layout? Generally, they are designed like this. Okay, here it will be VDD, there it will be ground. Okay, all the PMOSes will be sitting here, and all the NMOSes will be sitting over here. Okay, and all the connection you will make like this. Okay, so PMOS and NMOS are not sitting together. Okay, so you cannot diffuse. That's the rule that has been imposed on the standard cell layout. Okay, and that is the reason why we cannot diffuse that. And but if you ask me, can I diffuse N1 and N2? N1 and N1 you can put over here, and N2 you can put over here. Okay, lambda spacing rule. Okay, we will be discussing about the layouts in a greater detail, right? So lambda spacing rule and all. Uh, but the thing is, you cannot diffuse a PMOS and NMOS, because whenever you design a standard cell layout, PMOS is designed in a different stack and NMOS is designed in a different stack, and that is the reason you cannot do that. Okay, so in this particular case, the final node output capacitance will be 12C, as you can see over there. Now the question is, how do you find out the propagation delay? So let me draw the circuit for you. If you want to find out the propagation delay, you have to choose any one of these paths. Okay. So how do you do that? So if you want to find out the propagation delay, okay, the worst case propagation delay, the basic thing which you have to keep in mind, I will just remove all the sizes for you. Okay. And you have to, you should know, right? How are you finding the worst case propagation delay? So what do you mean by worst case propagation delay? This is the output node you are talking about. What is the maximum time for this capacitance to become zero? So that is my worst case propagation delay. Okay, so if it has to become zero, any one of this path has to be active. So that is, we know that. Okay, and it has to be worst, so only one path should be active, right? Because if both the paths are active, in this case, the logic is complementary, so it will happen. But in another cases where the logic are not complementary, the two paths are not complementary, you have to make sure that only one path should be active at a given time. That is that so How does it will help? It will make sure that it will be a worst case, right? Because if you have two paths, it won't be a worst case. Now the question is, which path should I active, this one or this one? Does anybody has the answer of that, or it doesn't make any difference? Any path you can take. Okay, so let me try to answer this for you. You have to choose that particular path for which the pull up capacitor, this is actually not isolated from the output node. Okay, so the thing is, these two should be on, and you have to make sure which path you are taking. So if this 2 has to be on, so this has to be 0 0, so this path will be activated, right? And why I have chosen this particular path, and see, in this case this will be off, right? If I choose this path, so the thing is, this 12C, this 12C capacitance will discharge from here. That is one thing. Okay, this 12C capacitance will be discharging from here. Along with that, this 8C capacitance will also discharge from here, right? So this is actually the worst case. So worst case is not only this 12C has to be discharging. If there is an internal node, if that is also coming into path, right, that has to discharge, right? So for having worst case, the input A should be 0, the input B should be 0. Okay, this is your worst case situation, right? Now let me draw the circuit for you, how it will look like. So it will be like, so these are the capacitor. Okay, I have to take any one of the path, or this path we have decided, right? Because there is a strong reason behind it why this path has been taken, right? Now if you see here, it is 2C capacitance, there it is 12C, right? Here it is 8C. Okay, now if I calculate using Elmore delay model, what I have to do, I have to find out at the particular output node. Okay, if I find out at the output node the delay, okay, so this will be what? So I have to start from this particular path, right? If you see what we have sized, this is 2, so this is 2. So the what will be the resistance? If we have sized 2, the resistance will be R by 2. Okay, so this will be R by 2. Earlier I have actually written 2R, that was the reason it was giving us confusion, right? So it will be actually R by 2. Here also it will be R by 2, right? And when what we will do, we will try to put the Elmore delay formula over here. Okay, so the delay will be this R by 2 times 2C, right, for this particular path. Okay, now if you see for this particular C here, 12C, how much resistance you have? This R by 2 plus this R by 2. Okay, so R by 2 plus R by 2. Okay, so this you will have, plus if you see the off path. Okay, so for the off path, what is the resistance for this particular path? If you see from here, okay, so this will be R times C. Okay, how many C? It will be 8 times C, right? Because that is the off path. So in off path, the resistance path is R, okay, and the capacitance is 8C. If you calculate everything, it will be 21 RC, right? So this is propagation delay falling worst. What we have done, we have applied the Elmore delay formula. Every time you calculate the worst case delay, you have to make sure which input combination you are taking, right? This is a small gate, but if you calculate for a larger gate, right, you have to first figure out, okay, what is the worst case input combination? Okay, which input combination is making us to discharge most capacitances? Okay, that's how you calculate the worst case falling delay. Is this clear, everybody? Okay, so I hope this is clear. Now I am moving to the second part, which is the falling delay. Sorry, this was the falling delay, which was 21 RC, right? If I see the in the rising delay part, I have to take one path. Okay, so I can take any one of this path. So I will just take one of this path. Okay, so if I take one path from here, so which path I should take? So I can take maybe B, and so I will make sure that A is open. So this is open, and B is also open. So this is there. So I will take this particular path from here to here. Okay. So this is like this, and such that in the ground also most of the capacitance is there. Okay. So what is this? This is B bar. This is A. Okay. Here this is A, and this is B. Right. So no, I think there is a problem in this. Okay, if this is one, so A is off. Okay, B is also okay. A bar and B bar. This path we are taking. Okay, so too much cluttering, right? So from here, this path we are taking. From here, this path we are taking. Okay, so we will just quickly calculate how much capacitance is over here. 8C, right? Here it is 12C, right? Here it is 2C. Okay, so we will go from like this, from 8C, how much resistance we have to see. So this is R by 2, this is R by 2. Okay, so it will be,
So one thing, sir, I just mentioned one thing that said A bar and A, P1 and P2 cannot be open simultaneously.
P1 and P2.
P2, both are A bar and A, both input are there. So if A is 0, then A bar will be 1.
Oh, just 1 minute. Okay, let me see. So if this is 1 and this is also 1, okay, then it is a problem. Okay, so the input combination should not be like that. So what I have to do, I have to make sure that one path is actually active. So I can take A as uh, A as 1. Okay, and if I take A as 1 and B as 1 for this particular circuit, so this will be off. Let us redo again. We have to make
Then P3, P2, N3, N4.
P3. Okay, just 1 minute. P3, P2, N2, and
N3, N4. N3, N4.
N3 and N4. Okay, so A will be 1. No, so if A is 1, then this will be off, right?
A is 0. If you take A is 0 and B bar,
A is 0,
B,
then this is 1. Okay, so this is on, this is on. Okay, and if your yeah, if B is 1,
sorry,
so this is 1, right? So this is, I think, correct, right? No, if B is 1, this will be 0. Okay, so okay, this part, so this won't be connected. Obviously, it should happen like that, right? Because VDD to ground path should not be there. So B is 1, so B bar is 0, A is 1, okay, sorry, A is 0. So the input combination is A is equal to, okay, so A is equal to 0 and B is equal to 1. Let us see on this, okay. If we will happen like this, what will happen? If A is 0, so this path is on. If B is 1, so this part is on. If A is 0, right, this is on. Okay, this is off. So this path you can directly discard. Okay, from here this is off. Okay, so the B part, so B is off. So in my diagram, this will be removed. Okay, It will be like this. So that's the complementary logic. You cannot have direct path from VDD to ground. Okay, so you can have till here. So this is 2C, this is 12C, right? And this point is 8C. So if you calculate now, this is clear, right? Hello, hello.
Yes, yes, yes.
Okay, yeah. Right. So R by 2 times 8C. Okay. Then R by 2 plus R by 2. So this R by 2 plus this R by 2, R times 12C. Okay, plus, so the downward path is R times 2C. Okay, R times twice C. Okay, so if you see, so this will be 4 plus 12, 16 plus 1 plus 2, 18 RC. Okay, so this will be your propagation delay rising. The previous one was propagation delay falling. Okay, why we have taken this combination? Because we have included this particular node. We wanted to include. Okay, that is the reason why we have taken this particular combination. So okay, then we will proceed ahead. Simple question. It's again a multiple choice. Which of the following are true for a double size two input NAND gate? Okay, so I have a two input NAND gate. NMOS PMOS is four times the standard NMOS and PMOS, both are. Okay, so if I have like this, which of these statements are true? Anyone? Okay, so let me tell you. So if you increase the size of both NMOS and PMOS, okay, so the first answer will be compared to the standard NAND gate, this gate has a relatively low propagation delay, okay, when some load is connected, okay. So if output load is connected like this, in which gate? Two input NAND gate, okay. So let me tell you, this is how two input NAND gate will look like, okay. This is VDD, this is ground, and this is C. Okay, this CL is actually very very greater than whatever the parasitic capacitance is over there. Okay, in that case, if you increase the size of this both NMOS and PMOS, okay, the first thing will be the falling delay will be reduced, right? Because if you increase the size of the transistor, the current will increase. We have also seen that the parasitic delay increases, but the thing is, this parasitic delay, whatever it increase, right, will be much lesser than the actual load. Okay, so whatever the increase in the parasitic delay will be actually negligible. Okay, in that regards. So it will have relatively lower propagation, the falling delay. So that is one of the thing. And the second thing is compared to standard NAND gate, it is harder to drive one input of the double size NAND gate. Okay, so if you have a NAND gate normal, right, and if you have a NAND gate which has double the size, right. So the thing is, the input capacitance of the double size NAND gate is higher, right? So it will be harder for you to drive the higher capacitance. Okay, these are the two correct statements. If you see all the other statements, those are actually not correct. Okay, the first statement is saying that for a standard NAND gate, this gate has relatively lower PDF and no load output disconnected. So this statement is not completely true. Why? Because if load is not there, then increasing the size of the NMOS and PMOS will also increase the capacitance along with reducing the resistance, right? So you cannot directly say that. Similarly, you cannot directly say that okay, it will have higher PDF. That also is not true. Okay, now if you see over here, compared to standard delay, it will we have relative higher. No, it will be lower, right? Because load is there already. If you increase the size, the current increases, eventually the delay will reduce. Okay. And we will use the double size NAND gate when we want to reduce the delay of the circuit at the cost of the area used. This particular point is also not correct, right? Because you have to make sure that if load is connected, then only this particular statement will be correct, right? If load is not connected, this statement is not correct. Okay, so the correct statement are only C and F. So should I proceed ahead? Okay, very simple question. The PDF of an n input NAND gate propagation delay is given by this equation, Elmore delay formula. The thing is, you have to find out, okay, what will be alpha, beta, and gamma. Okay, so let me do this for you quickly. So this is what an input NAND gate. Okay, so an input NAND gate will look like this. This is an NMOS, okay, not PMOS. So this is how an input NAND gates will look like. Okay, so if you see the propagation delay, so before seeing the propagation delay, what you have to do, you have to size this. Okay, so this will be 2. All of this will be 2, right? Because that's how the NAND gates are built. It doesn't matter because at any one of the path, one of the NAND gate is activated, so you have to size it 2. And if you have n such gates, the size will be n. Okay, if you remember, if there was only one, it was 1. Okay, if it is 2, then it will be 2. It will be 3, then it will be 3, right? Because 3 will be result in 1. Okay, so the output node, if you see, okay, will have n from here, this capacitance, okay, plus twice of n from all the PMOSes, okay, twice of n from all the PMOSes, okay, times C. So this much capacitance output node will have. Okay, if you see from here, this particular node will have NC. Okay, similarly, all the nodes will have N times C capacitance, right? Whatever the size of the transistor you will have. Okay, and if you see what is the resistance over here, R by N, here also R by N, and here also R by N, right? So this resistance will be there. Okay, because all the paths will be divided, the resistance will be divided into R by N, R by N, R by N, right? If the total resistance is R. So up to this we have. Now what we will do, we will find out TPDF, right? We will try to write a formula. This formula will be from, we will start from here, R by N multiplied by NC. Okay, similarly, if we go just above of this transistor, it will have R by N plus R by N. So 2R by N times NC. Okay, it will just sorry, it will just go on. So for the last one, NR by N into NC. Okay, plus so this will be 2n plus n, 3n. So 3n RC. Okay, so this is how I think it will be. Let me just check. So R by N, R by N. Okay, so for last one, it will be actually n minus 1, right? Because this particular point will be n minus 1, not n. Okay, so if I add 1n from here, this particular path, so this will be actually 2n. So the last one actually become the nr by n into nc, right? So I have divided this 3 nrc into nrc, and so why I have divided, because it will actually form a linear expression. Okay, so if you see from here, so it will be like this: R C plus 2RC plus NRC, I guess, yes, plus twice NRC. Okay, so it will be like this, and if you will actually calculate everything, the final output you will be getting will be RC times n square plus 5n divided by 2. So I've actually calculated. Okay, so this is RC, so gamma will be equal to 2. Okay, alpha n square, so this will be alpha will be 1, and beta n, right, so beta will be 5, 152. Using this, a homework assignment is for you. You should go and you should find out for an input NOR gate and XOR gate. Okay, what will be the generalized equation if you have an input NOR gate and XOR gate, right? For NOR gate it is easy to find, but for XOR gate you have to see. Is that clear? Okay, so we will see the next question. So this up to that was for the week 4. This is for the week 5, right? I'm trying to catch up actually, which I have already said, right? The question here is, in the first diagram, a custom logic gate is described, which contains a unit NAND gate followed by a NOR gate. So this is a unit NAND gate followed by a NOR gate. Okay. So if you see over here, a circuit is made using sorry, circuit is made using two of the above custom logic and a and a unit inverter. Okay, so this custom logic cell is here, right, and there is a unit inverter over here. Okay, the question that has been asked is, find the frequency of oscillation of the circuit, and you must enter the following parameters. What are the parameters? For two input NOT gate, the rising delay and falling delay is 0.25. For two input NOR gate, rising delay and falling delay is 1.25, and two input NAND gate, the rising delay and falling delay is 1 nanosecond. Okay, so this is the question. Anybody has any idea how to approach this question? So anybody wants to tell me how does this circuit will work? What kind of circuit this will work? It has said that you have to find out the frequency of the oscillation. It means it will actually work as a oscillator. Okay, and whenever you are designing a circuit for actually working as an oscillator, you have to have odd number of stages. So that is the first thing you have to see, right? So here if you see, right, one stage is this, and in each of the custom cell there are two. Okay, so total 5 stages, and it is an odd number, so then only it will work as an oscillator, otherwise it is not. Okay, and you know that this is nothing but an inverter only. All of these are inverter, and this is an unit inverter. Okay, so if I want to find out the frequency of oscillation, this will be 1 by 2 times propagation delay, TPD. Okay, this I have to find out. Okay, so to calculate this, I just have to see the critical path. This is my path. Okay, and if you find out TPD, this is the custom path. Okay, in the custom path I have two custom cells. Okay, so if I see only the NOR gate, not NOR gate, first NAND gate. Okay, there are two NAND gates in this path. The circuit will look like this. This is how the circuit is actually going to look like. Okay, this is Y, this is input, this is my output. So it's a 5 stage, and the circuit looks like this. So what you have to do, you have to find out the propagation delay. So if you see, this is my NAND gate, so this will be 1 nanosecond. Then it is a NOR gate, okay, this will be 1.25 nanosecond. Then it is an inverter, 0.25 nanosecond, okay. Then again a NAND gate, 1 nanosecond plus 1.25 nanosecond, okay. So if you see, it will be 1 plus 1 2, and 1.25 plus 1.25, this will be 4.5, okay. So 4.5 plus 0.25, this will be 4.75 nanosecond, okay. So this is actually 4.75 nanosecond, and if you have find out f oscillation, this will be 1 by 2 times 4.75, okay. So you will actually get some frequency around 105, 105 megahertz, okay. 1 by 2 into 4.75. So this is how you calculate the delay of this particular circuit, okay. So if you have provided with the delay of all the individual gates, you just add it, and you find out the frequency using the total path delay. Any question in this? Okay, I'm going fast because you're not asking question. So a simple question again. I have two gates A and B. The size of gate A is given 12. The size of gate B is given 15. Right? I have to find out what is the relative size of PMOS, NMOS, PMOS, NMOS of NAND gate and OR gate. Can anybody quickly tell me what will it be? Because we have just seen the logical effort, right? So in the logical effort, we have seen the sizing before logical effort. We have seen the sizing. How do we size? So if the total size is A, right, what will be the size of NMOS and PMOS?
So for NAND gate,
Yes.
uh, this A is 12. For
For,
NAND gate,
for NAND gate, it will be
NAND gate it will be 2 PMOS. Just a minute. Just a minute.
okay. Other students can also try. So this, and
2
then
by 3 into 12 for
mhm,
PMOS,
okay,
it is 8 for NAND gate, and 1 by 3 into 12, that is 4. 8 for NAND gate, it will be 8 and 4. 8 for PMOS, 4 for NMOS.
okay.
Oh, sorry, sorry. No, 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 no. Just I mistake. Sorry.
I missed it.
It is 4. Yes, 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 yes. It is wrong. It is 6, 6. 6, 6. It will be 6, 6.
For NOR gate, it
Sorry.
will be 8.
Yes, yes, yes.
Okay.
I
So
missed
let
it.
me tell you how this has been calculated. This is how your NAND gate looks like. So this is my PMOS, two PMOSes, and then two NMOSes, right? The sizes are 2, 2, 2, and 2, right? So if the total size of an input, right, so is 2 plus 2, 4, okay? So individual contribution of PMOS and NMOS are 2 and 2 only, right? So if the total size is 12, right? So for PMOS, it will be 2 by 4 into 12, okay? And for NMOS also, it is 2 by 4 into 12, right? So 4 3s are 12, and so the answer will be 6 and 6. Similarly, for NMOS, sorry, not for NMOS, for so this is for NAND gate. If you go for NOR gate, it will be 1 and 4. Okay, so I'm just directly writing it 1 and 4. If you remember, it was like this. if you remember it correctly, we have done today. Okay, so the size was 1, then 4 and 4. So any of the input will have 5. So total it will be 5. Okay, so if I want to divide it, so for PMOS it will be 4 by 5 into 12, sorry, into 15. Then for NMOS it will be 1 by 5 into 15. Okay, so actually it is 15, so it won't be 8 and 4. Okay, so this will be 4 3 is 12, and this will be 1 by 5 into 15, this will be 3. Okay, so if the size was 12, then it would have been 8 and 4, but in this particular case it will be 12 and 3, so the total size will be 15. Okay, this is how you attempt this particular question. Any doubts here? Okay, no doubts. Moving to I think this is the last question we have. Just see. Yeah. So assume that you have to come up with a purely combinational circuit, right, with 100 logic gates to execute some logic. However, this circuit fails to meet timing requirement as the delay is greater than the requirement. Okay, please understand the question. The question has given that, okay, you have to make a circuit which has to work in x nanosecond, right? X can be say 10 nanosecond. Now the circuit which you have designed is not meeting the timing requirement. It means the circuit has some delay, that is y nanosecond, it is greater than x nanosecond. It means our circuit, say suppose, has 15 nanosecond instead of 10 nanosecond, right? The question that has been asked over here is, what are the following, or which of the following will definitely not help to reduce the delay of the circuit? Assume that you do not have any area and power constraint. Okay, there are 5 options. You have to figure out only one or two, whatever multiple choice it is, right? Those that option which will actually not help in reducing the delay of the circuit. Okay, the question is clear. Anybody wants to tell me which answer is correct? I will repeat the question for you. There is a combinational circuit which is supposed to work in 10 nanosecond, but it is not working. It is working in 15 nanosecond, right? Now I have to reduce the delay of the circuit. Which of this option will not help in reducing the delay? Anybody? Anyone? It's a simple question, not that difficult. Okay, so the answer over here is, let us see. Okay, the first answer which has been given over here, or the first option we have, is changing the clock frequency of the circuit. Okay, now the question is, right, if I change the clock frequency of the circuit, will it help? The answer is no, right? Because clock is an external signal which is coming. Now what you have to do, you have a combinational circuit which has to work in a particular time period, whatever time period which you have, right? And if you change the clock frequency, if you reduce the clock frequency, right, it won't help us meeting the timing requirement. The clock should not change, right? Because clock is the timing requirement. What do you mean by timing requirement? It has to work in this particular time. So that is actually decided by clock. Changing the clock frequency doesn't help in reducing the delay of the circuit, right? Because you're not changing anything in the circuit. You have to change some parameter of the circuit itself. So it is definitely an answer of our question. It won't help. Okay, we will, if you move to second part, analyzing the fan out of the gates in the circuit and trying to reduce the fan out. So what do you mean by fan out? Fan out means how much output load it can derive, right? Or how much output capacitance it has. Okay, so if you reduce the output capacitance, the output load, okay, it will increase the speed of the circuit. So this is a correct option, that okay, it will help in reducing the delay. Okay, so for us it is the wrong option. Okay, now analyzing the critical path and trying to optimize the number of gates. So this option is what is saying that, okay, I have a path, just like I have shown in the previous one, this one. I have a path, I have a 5 stage. What I will try to do, I will try to reduce the number of stages, say, right? Or I will try to change the number of transistor, or reduce the number of transistor. The question is, will it help in reducing the delay? Yes. If you change the circuit, right? If you optimize the path, yes, you will be able to reduce the delay. So again, this is also not our answer. Okay, there is only one answer till now. Now combine the multiple NAND gates into single complex gate, right? So if you have, say, multiple NAND gates, which is in series of stages, right? It will have individual fan outs or individual capacitance of each of them, and it is actually cascaded. If you make only one, a big one, right? It can happen that it will be able to reduce the delay. The output node capacitance might reduce. Okay, so this can also be an option to reduce the delay, and try to minimize the number of logic gate by using inverted logic. Okay, so instead of using and or, if you use and or, you have to actually use 6 gates, oh, sorry, 6 transistors, right? If you design and, but if you design NAND, you have to use 4 transistors. Okay, so if you design all your logic using NAND and NOR gates, right, the number of transistors required will be less. Okay, so this will also help us in reducing the delay. So this is also not the answer. The only the answer which we have, which will not help us in reducing the delay, is the clock, because clock is an external signal. Anything else which has been discussed over here is will in some way help in optimizing the delay of the circuit. Right, now if I'm talking about clock, you have to talk about the sequential circuit. So as of now in the class also, I think we have not discussed the sequential circuit till now. So it will be coming into I think couple of classes later. When we come to sequential circuit, we'll have a detailed discussion of clock. Okay, so I have tried to cover a couple of questions from this week. Okay, maybe from next week I will cover all the question, and then follow the next week question, such that uh, we will have one discussion before your assignment submission. Okay, so if you have any question, you may ask. Right, from my side, yeah, today's lecture is over. Okay, so if you do not have any question, thank you for joining today's